after alcohols, the next logical thing we're going to talk about is about carbonyls or carbonyls, or whatever you prefer to call them. Now, they characteristically look like this. So carbon double bonded to an oxygen, and then whatever else over here. Now, our group can be an alkyl group or hydrogen. So if the organic molecule has the carbonyl, which is double bonded to oxygen. Now, there is something interesting here. If you've ever heard of the term oxidation associated with combustion, you'd think, hey, so that would be more and more oxygen. Now, what happens when you start off with, say, an alcohol? It has to be either a primary alcohol or a secondary alcohol, because otherwise this doesn't work. So if you add more oxygen, what happens is that this, well, the hydrogens come off and you get this, plus water. So, what does this say? This says that an aldehyde or ketone is considered more oxidized than an alcohol. Now, an aldehyde has it at the end, has the carbonyl at the end, or alternatively at both ends. Think about this. Methanol. Methanol is the aldehyde that is based on methane. Does it have ends? Well, technically, no. It's just C, double bond O, H, and H. So, this is also called formaldehyde. The dilute form of formaldehyde is called formalin. You may be interested, given that formaldehyde is used to preserve animal specimens, to know that formalin used to be used to help preserve milk. And, well, the campaign to remove that from milk really only started in the 1890s, when the Chicago Milk Inspector started a campaign against formalin by issuing a press conference that was like, "Formalin, the chemical used to preserve milk, will kill a cat. What will it do to a child?" So, well, eventually this worked out, and the toxicity of formaldehyde became publicly known enough that it was recognized exactly how stupid it was. But the thing is, it was actually valid compared to the sort of bottles that they were using at the time. They were using rubber tubes that led into bottles. These bottles were called murder bottles later on. Why? Because the rubber tubes were long, hard to drink through, and very hard to clean, which meant that a lot of children died of childhood diarrhea because of it. Now, ketones. Ketones are organic compounds that include this on a secondary carbon. Now, I am aware that usually R is used only for alkyl groups. So here, R is alkyl, not alkyl or hydrogen. So, why is it that aldehydes and ketones are considered differently? Well, it's because aldehydes can be oxidized further. How do we oxidize it further? Well, if we started with an alkane and then oxidize it one step, that's an alcohol, right? So you add it in between. What happens when you take an aldehyde, where this part is whatever, and oxidize it further? Well, you add an oxygen here in the middle and it becomes a carboxylic acid. So carboxylic acids have quite different properties from aldehydes because they are acidic. Now, humans are fairly sensitive to chemicals with carbonyl groups. For example, many perfumes and other odors contain them. Let's think of some cases. Well, okay, there's safranal, which is used in the spice saffron. It gives the spice its flavor and scent. Now, saffron is because of the way it's harvested, which is to take the stamens of crocus flowers and dry them. Because of that extremely labor-intensive harvesting method, it has a unit price approximately equal to silver in terms of per unit weight. This is the most expensive spice in the world, and it's basically just an exhibit of, hey, look at me, I'm attention-starved and rich, for the most part. Now, what is the second most expensive spice in the world? This may amaze you, given it is one of the most common spices. Vanilla. The vanilla bean is relatively labor-intensive to harvest, and the reason why it is second most expensive is because a lot of people, basically everybody, can have a taste for vanilla. Now, what does that say? Well, it says something very sad then, that vanilla in English is considered a slang term for traditional and boring, given that so many people like vanilla that it is the second most expensive spice on earth. Now, vanilla's flavor is from vanillin. You are free to research it yourself on chemical properties and such. So, in terms of naming aldehydes and ketones, aldehydes very literally end in -al. They can also end in dial. But if you have 3 aldehyde groups, you typically do not call them trials. Why? Well, let's think about this. If I have a main chain, and then I have a side group that's also an aldehyde, then I would most likely name this part as per the ketone convention, because this is going to get treated as a substituent. Now, of course, this is a little bit hazy in terms of conventions. There isn't that much definite statement on this, but, well, naming it as a ketone style substituent, which would be oxo. So this could be oxomethyl, and this would be, well, let's see which end ends up being the lower total. So total we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And since this is 5, from the other end it would be number 6. So 5 oxomethyl, and this is 10 in total, so that's decane as a base, so decal. Except it's a dial. So decadiol. Now, why is it that we didn't have to state the positions of the dial? It's because we know it has to be at the ends. Now, here, given the fact that the orthoxomethyl group is very well known as 4-mel, you could probably get away with calling this 5,4-mel decadiol instead. Now, we should point out that aldehydes have higher priority than ketones in naming. Why? Well, it's because aldehydes can be reacted further to make carboxylic acids relatively easily. And that's a huge change in chemical properties. Whereas ketones, they do not react further nearly as readily, which means that they aren't quite as important. We don't need to pay quite as much attention to them. So, ketones end in -one, so you have di, tri, tetra, and penta, and hexa, and so on. So ketones, well, there's really no limit as to how many ketones you can potentially tack on to a molecule in theory. In practice, this is a bit of a no. in theory, you can have something that looks like this. And this is going to be, well, okay, there are 9 carbons. So this would be nonaheptone. Why is it that I didn't bother labeling the numbers? It's because with nonane as a base, the most you can have is 7 carbonyl in terms of internal positions. The ends would make this an aldehyde. So, because there are only 7 positions and we filled all 7 positions, we don't have to specify the positions. Although, I mean, really you should, but you can get away with this because there's no other spaces. There's no other options. This is it for the possible molecules that this can represent. Of course, if this was hexone, then that would be very different. Because, well, where's the empty space? Or rather, where are the occupied slots? So, if we have a ketone, we name it by oxo, which means that if we want to do another example, this here is 1, 2, 3, 4, 5, so it's a pentanal, and it has an oxo substituent. So this is 1 because aldehydes are numbered 1 unless it's symmetric, i.e. on both ends, and there you number to get the least total. So 1, 2, 3, 4, and thus this would be 4 oxopentanal. Now, properties of aldehydes and ketones. Well, aldehydes and ketones have polar bonds because we know that the carbon-oxygen bond is polar. So they have some level of polarity. They will bond polar molecules. And can bond nonpolar molecules. Now, if you have something like formaldehyde, that's not going to be particularly good at bonding nonpolar molecules. Why? Because it's just CO with 2 hydrogens. That means the overall particle is very polar. Whereas, well, if you have, say, an aldehyde group at the end of a relatively long chain, like say hexanal or heptanal, that will have a large nonpolar component, which will tend to bond nonpolar substances. Now, some reactions that involve aldehydes and ketones, when we form them, we use controlled oxidation, which, as I illustrated earlier, essentially takes this and changes it to this plus H2O. All right. The R groups here can be either alkyl or hydrogens. This would give a ketone or an aldehyde depending on circumstances. What happens if we go further? Well, we'll cover that next section when we get to carboxylic acids. If we hydrogenate, well, what do you think happens? I mean, we add hydrogen, so clearly this double bond has to become, well, go back to being an alcohol, or be converted into the appropriate alcohol. Now let's do some examples. All right, so for the hydrogenation of aldehydes and ketones, well, if we know that controlled oxidation does this, the reverse process is, well, we add hydrogen, and of course it goes from an aldehyde or ketone back to an alcohol. Now, Unlike, say, Markovnikov's rule, the alcohol group does not so much as twitch. It stays exactly where the aldehyde or ketone used to be and where the initial alcohol, if you started with an alcohol, used to be. So, example 1. First of all, we should note that no spell check program will ever like your chemical names. So when you're writing a chemistry report, make sure that you check carefully. And not just like, oh, it doesn't like my names and therefore I must check the names carefully. You should also check the rest of the text carefully, because I know full well that most of us who use word processors tend to rely on spell checking programs a little bit more than is strictly healthy. Now, name the reactants that are required to produce each of the following compounds. Then illustrate the reactions using structural formulas. Alright, pentanone. This can be 2-pentanal. Well, pentanol must be distinguished by pronunciation from pentanal. This is very important, because otherwise you can make all sorts of verbal mistakes in communications. So it's 2-pentanol or 3-pentanol. Now, for 2-pentanol, that's and plus concentration symbol oxygen, so oxidizer. And this leads to 2-pentanone. Now, there are two conventions that you can follow for writing out the names. You can write it underneath at the risk of mix-ups with the next row if you don't have enough space. Or you can write it beside, which we'll do for this next one. 3-pentanol. That is this. And then plus oxidizer. And that gives us 3-pentanone. Pentanone. So, we see the difference here is that you save horizontal space versus saving vertical space. We do point out, though, that if you're going to have more steps, it's usually better to write it underneath, because you don't want to get in the way of the next arrow or something, do you? But of course, we don't have more steps here. So, we should now name the products resulting from the hydrogenation of each compound, and then illustrate using structural formulas. So, ethanol it's actually usually better to illustrate before you draw any names. Why? Because for most substances, when the reactions are relatively complex, you don't want to name anything until you absolutely have to, because names are irritating when you get to big organic compounds. Ethanol, that's this, plus hydrogen, and this leads to ethanol. B, if we have butanone, well, we know that it can be either of these two carbons, but since the stereochemistry and such is all the same, well, it's the same compound. So this plus H2 leads us to OH. So this is 2-butanol. All right. So predict the products of the controlled oxidation of the following isomers. hexane 1O, hexane 2O, and 2-methylpentane 2O. So, since we don't have to draw any names, we can just go nuts with our structural diagrams. Hexane 1O. First of all, hexa, and 1O, OH. And controlled oxidation. Why controlled oxidation? Because if we went any further, we would end up with a carboxylic acid. So, instead of, say, ethanoic acid, also known as acetic acid, which is used in vinegar, for ethanol, we would end up with, for hexanol, we would end up with hexanoic acid. So, here instead, we use a controlled oxidation, and we get hexanal. We are not naming it because they said predicts the, we said predict here predicts the products, and well, we did predict the product. A structural formula is still a prediction of a product. We don't have to name the products. Which is one of the reasons why many students tend to like this type of problem, because they aren't asked to predict anything. Plus, that's this, 2-hexanone. And next we have 2-methylpentane 2O, which means that, well, first we start with a pentane base, and then 2-methyl 2O would be like this, plus controlled oxidation, and that leads us to, well, there's no hydrogen here to be removed. So this cannot form a double bond. And that means no reaction. This is the common abbreviation of reaction in English-speaking textbooks. So, in summary, if a carbonyl group is attached to at least one hydrogen, i.e. it is at the end of a carbon chain, then the compound is an aldehyde, unless it has a carboxylic acid or acid derivative at the other end, in which case that takes priority and the aldehyde is considered an oxo substituent. Now, if the carbonyl group is attached to two carbon atoms, so in other words, in the middle of a carbon chain, then, i.e. not at the end, not necessarily right in the middle, but just not at either end, then it is a ketone. The names are suffix -al and -one, respectively. Now, the carbonyl group makes organic molecules polar. This gives them higher boiling points and greater water solubility than the corresponding alkanes. Now, water is a very polar solvent. It will not dissolve nonpolar substances well. Nonpolar substances include, for example, hydrocarbons. What happens when the hydrocarbon components of a ketone or an aldehyde grow bigger? Well, then it gains more hydrocarbon-like properties. So the boiling point gets closer to the corresponding hydrocarbon chain, unless, of course, you add more carbonyl groups. And the water solubility also drops, unless you add more ketones or aldehyde groups to keep it balanced. Now, the controlled oxidation of a primary alcohol, so the alcohol is at the end of a carbon chain, will produce an aldehyde. If the alcohol is somewhere in the middle of a carbon chain, i.e. a secondary alcohol, then it's a ketone after controlled oxidation. If it's a tertiary alcohol, though, no reaction occurs. Why? Because the tertiary carbon is already bound to 3 other carbons. So how is that oxygen going to form a double bond? It's not. Therefore, no reaction occurs. It does not readily undergo controlled oxidation. On the other hand, uncontrolled oxidation, well, I point out that tert butyl alcohol is still combustible enough. All alcohols are combustible. So uncontrolled oxidation, that's another matter. So the hydrogenation of an aldehyde will produce a primary alcohol. The hydrogenation of a ketone produces a secondary alcohol. So this is the reverse reaction of controlled oxidation. Technically, this counts as reduction, which is the counterpoint of oxidation. Now, I point out that aldehydes and ketones are combustible. Why? Well, okay, it's carbon, hydrogen, oxygen in some combination. Can this be reacted to make carbon dioxide and water and release chemical energy? Well, yes. So that's it for this section, and we'll see each other again later.